last few minutes. The one related to the bandpass filter that will pop up is resonance. So we've talked about RLC circuits all along, right? And with our RLC circuits, up until this point, we've typically said either it was a DC supply, and we looked at the transient response, that was the stuff we did in Chapter 8, or we've treated it as a phasor, and we've done it in Chapters 9 and Chapters 10. We've just looked at it with a constant frequency, and we just see the output. And so we just turn each of these into their impedance, and we let them be. But now we want to look at the full behavior for variable frequencies. So now our input is some unknown frequency. It's just some input, Vs. So we need to find the transfer function that tells us the behavior when it comes out. And so when this happens, you'll notice that there's an inductor and there's a capacitor. Well, inductors, when we go to phasor form, are positive J something, and capacitors are negative J something. So there's a particular omega that will make the capacitance cancel the inductance. Those J terms will disappear. And at that point, our circuit looks like it is purely resistive. That is the point where we are at resonance. Because there's no energy being stored up in the inductor and capacitor. They're balancing each other perfectly. And all of the power is going through our resistor. So we can find that resonant frequency. It shouldn't be surprising. It turns out to be 1 over the square root of LC, which is exactly the frequency, the natural frequency we found when we did the RLC circuits in Chapter 8, right? If we want that in hertz, we can find that, of course, with the factor of 2 pi. And again, just going through this circle, letting omega be a variable, here is the expression for the impedance of this circuit, which is the transfer function, effectively. Because if I had the output over one of these capacitors or something, right, I could divide by the input. So when things are in resonance, remember that our impedance looks resistive to our supply. The supply voltage and the current will be completely in phase. There's not going to be any power factor between them. Cosine of theta is 1, right? Again, that's the whole point. When it's resistive, there's no phase shift. We also find that the magnitude of the transfer function, which is the z of omega, is at its minimum at that point. Right? Also, it's important to note that at that resonant point, it's possible for the voltage on the inductor and the capacitor to be much, much higher than the source. Why is that? What is resonance? It's like when you're on a swing, right? And you pump the swing, right? If you pump it at just the right frequency, what happens as you move your legs in and out? But what happens to the swing? And you on the swing? I have little kids. I've been on a swing set probably a lot more recently than all of you have, right? Yeah, it swings farther. So you're like a little pendulum, right? And you're just swinging back and forth. And as you start to pump your legs, right, it starts to go higher and higher and higher. My kids love when it gets to that spot, and then they start to scream. When it starts to get a little wobbly at the end, right? Because you've hit resonance. That's a pendulum. There is a natural frequency based on your mass, right? So my natural frequency is much different than yours, right? But when you pump the swing at that frequency, in fact, you add energy to the circuit every time. Add energy to that pendulum every single time. Or when someone pushes you, right? And you push the person right as they're taking off. You give them a little shove, and they go a little bit farther, and then they come back. If you push them like as they're coming back, and you push them, what happens? Stop. Yeah, it just like very quickly collapses and does nothing, right? Because you put energy in at a different frequency than the resonant frequency. And so it dies away. So that as you're adding that energy in, that extra energy you're putting in can result in much higher voltages and currents in your inductor and capacitor. Because they're building up energy, storing it, saving it, giving it back and forth to each other, and that can result in really high voltages. So it can cause problems to reach resonance in an electric circuit, because if you exceed the voltage threshold of your component, poof. We had a little fun yesterday. We exceeded the amperage current of someone's wire in the lab yesterday. Plugged it into the quadcopter, and it instantaneously went poof. And there was a nice little cloud of smoke as all of the insulation on that wire evaporated in 1 second, right? So you remember, you want to be careful, right? You don't want to exceed those voltage and current thresholds. But anyway, so with resonance, that's a big issue as well. But at the same time, it provides us that sort of band pass functionality. There's a peak where we can get this circuit to have, to look like a pure resistor. Again, you can find the bandwidth. The bandwidth is just found by taking these points where we're at roughly half power. So figuring out sort of the half power width of the peak in the transfer function if you're looking at the Bode plot. And then you can also calculate, of course, the average power and then the maximum power that are transferred through the circuit, which occur, of course, when you're at resonance. When you're at omega equals omega naught. Right? The equations are there in the book for you to go through and look at how to calculate those half-power frequencies so you can actually find those points. And then the nicest thing to remember is that the bandwidth is just the difference between those half-power points. And a few other nice things that we calculate are things such as the quality factor, which is the sharpness of the peak, the bandwidth, which is the width of the peak, right? And you can find all of those through this nice little relationship right here, that the bandwidth is equal, which is equal to the resistance over the inductance, is equal to the natural frequency divided by the quality factor. So if somebody often will tell you that they have a resonant circuit or a filter of a very high quality, high Q. When you're building resonators for cell phones, you need a high frequency resonator, you need a high Q factor. They'll say that, you'll hear that a lot, like 10,000 or more. And that, you can use that little equation right there to then figure out, oh, what does that mean the inductance and the resistance are? What is the bandwidth of this thing? You can figure all of that out when you know just a little bit about the circuit. Again, know like 2 of these and you can figure out all the rest by plugging them into the formula. So hopefully that's enough to get you guys through the end of chapter 14. There's an example, parallel. We might touch on it again if we need to, but start working on the homework. And I think if you have questions on these resonant parts, that'll be the best time to come back and revisit it. All right, I want to start talking next class a little bit about chapter 15.